So currently we are considering plume with fixed volume release or fixed buoyancy release, as we checked that in the previous lecture, which in reality looks something like this, right? So we are assuming that a fixed buoyancy which has fixed volume and fixed reduced gravity, that is released, and it's not a continuous release, right? So that is released at once, and that now goes up or goes down depending on the density difference. uh, in the process, it also mixes with the ambient, and the density or reduced gravity of the plume decreases, whereas volume increases, right? And we have been trying to derive volume conservation, which by considering r to be the radius of the plume, we were able to derive this equation: dr by dt is equal to a w bar 3m, where w bar is the mean velocity of the plume in the vertical direction, and a and m are the constant. Another equation that we derived was related to momentum conservation, where we balance the rate of change of momentum with the difference of buoyancy force and gravity force, right? And that gives us uh, this particular equation, where f naught here is the source buoyancy, that is the fixed buoyancy that is released with the plume, and v is the time at any time t, and t is just the time here. So v here is a function of time. Okay, so now let's go further and try to derive the solution for plume radius, plume volume, and other parameters with time and with elevation. Okay, so now we have got these two equations, equation number 1 and equation number 2. Let me copy equation number 1 as well, so that we can compare these two side by side. Okay, so these are two equations we have derived using volume flux balance and momentum flux balance. All right, so here now we know that we have derived an expression for w bar in equation 2, so we can replace w bar in equation 1 using equation 2. So we do equation 2 to equation 1, and that gives us dr over dt is equal to a over 3m, w bar is 2 by 3 f naught t over v. Okay, where v is something we know, v is mr cube, so that gives us dr over dt is equal to 2a over 9 m square f naught t over r cube. Okay, we have replaced v with mr cube, and that is something we already defined in the previous lecture. Okay, so that is something we have so far, and now what we will do the separation of variables, and it gives us r cube dr is equal to 2a 9m square f naught t dt, right? And here, except r and t, everything else is a constant, and that is why we can simply integrate it, and that will give us r to the power 4 over 4 is equal to 2a 9m square f naught t square over t plus, let's say, constant c2. Okay, so now for an ideal plume, we assume that we did for the previous case, v is 0 at t equal to 0. In same way, if v is 0, r can be considered 0 at t equal to 0. This is for an ideal plume, okay, where in case of ideal plume, you only have buoyancy. So basically 0 radius, 0 volume, but infinite reduced gravity. So by applying this condition, we can from this equation get c2 is equal to 0. So basically This condition implies that C2 is equal to 0. Okay, and that is why your r to the power 4 becomes simply 2a over 9 m square f naught t square over t over 2, where obviously these 2 cancels. So this gives us a relationship between r and t of the form 4a over 9m square f naught 1 over 4 t to the power half. Okay, so this is the rate of change of radius with respect to time. Okay, so r is the plume radius and t is time measured from the point of release, right? So the moment you release buoyant fluid, that moment is t equal to 0, but then you start measuring time from there, and that gives you the radius r from for given particular time. Okay, so this is the formula we get for the radius. And now, having derived a relationship between volume and radius and other parameters, one by one we can also estimate or get formulas for other parameters. So let's do it for plume volume first. Right, and this one is something we have defined as mr cube, right? That is what we did in the last lecture. So if we do that, we use this formula for radius from here, that will give us the volume formula as 64 a cube f naught cube over 729 m square 1 over 4 t to the power 3 by 2. Okay, so this is the formula for volume flux. Volume, not flux, the total volume of the plume at any time t. Okay, this is plume volume at any time t. Okay, where a and m are the constant that we have to find out experimentally, and f naught is the source buoyancy at the release. All right, so that is the plume volume, and similarly we can find other parameter. So one thing we have already seen is the reduced gravity. For reduced gravity, we know that it is related to f naught as q naught g prime naught is equal to v times g prime. Let's call it g prime bar, that is the mean reduced gravity, right? So q naught is the volume at the release, g prime naught is the reduced gravity at the release, and whatever buoyancy we had at the release is conserved at any other time, right? And that is why to find g prime bar at any time t, we can simply divide f naught by v of t, and v of t comes from this equation which we just derived. Okay, so this gives us an equation of the form 729 m square 64 a square f naught 1 over t to the power 3 by 2. Okay, so this is how your reduced gravity decreases with time. Okay, it's decreasing with 3 by 2 power of time. Okay, and f naught, as we note here, is the source buoyancy at the release, and that is a constant value. Okay, I can also note here that f naught is constant. Okay, so that is the reduced gravity, and by reduced gravity actually you can get rho A minus rho P bar over rho A times G. So this will give you rho P bar as rho A G prime bar over G rho A minus this. So that is your rho P bar. So that is the plume density at any point of time, mean plume density, right? And if you know the J prime bar is decreasing with time, your total density of the plume is also decreasing with time. Now, by considering one of the equations that we derived, we can also find the plume velocity. Okay, so mean vertical velocity of the plume. Okay, that is W bar. So to find W bar, we go back to this equation number 2, right? And we see that this is related with F naught T and V of T. Okay, so we simply copy that here, copy and paste, right? So this is the formula that we already derived, and we have the formula for V of T as well, which is coming from here, right? So if we use this V of T formula, this gives us the W bar as there is probably a small mistake. Okay, I think that is correct. That will give us 9m square over 4a cube f naught 1 over 4 1 by t to the power half. Okay, so this is the mean vertical velocity of the plume, with which the plume is rising upward. Okay, either rising upward or coming down in case of a denser plume. Okay, and why we keep calling mean velocity? Because we know that at the center of the plume, velocity might be different than at other points. So at each point it might have different velocity, but we are more concerned about the mean velocity. We don't want to consider the behavior at each point. Rather, we consider it all points together. Okay. So that gives us the vertical velocity. And now let's try to find the position of the plume. Okay. Position of the plume. So as we have seen, if let's say this is a point where plume starts, so it actually moves, it becomes bigger and bigger and moves vertically up, right? And if this is z equal to 0, at t equal to 0, this has attained z1 at t1, z2 at t2, z3 at t3, z4 at t4, etc., right? So it is continuously moving upward or moving away from the injection point, if this is the injection point, right? So if you want to find where is this plume located at a particular time, okay, so we can actually use the dz by dt is equal to w bar. This is basically the vertical velocity, right? So if you want to find the location, you simply integrate the vertical velocity and that will give you the location. All right, so if we integrate it, that gives us z as w bar times t, and w bar is something that we have just found it here. So 9m square 4a cube f naught. So this particular part is constant, so it becomes dt over t to the power half. Okay, and this will give us, if we integrate, uh, here we can also assume that there is constant c3 after integration, which actually will become uh, at t equal to 0, z is equal to 0. That implies that c3 is equal to 0, right? So we apply that boundary condition, and with that we get z as 36 m square over a cube f naught 1 over 4 t to the power half. Okay, so this is the position of the plume at any particular time t. So if you want to find how far it has risen starting from the point of release, this particular equation can be used. Okay, so and you can see it all depends on the value of f naught. If you know the buoyancy at the release, you can actually predict its location or moment depending on the time. All right, so these are different equations we have derived, and now we can find relation between uh, radius of the plume at different locations also. So far we have been trying to find everything with respect to time, but what if we want to find them also with respect to the location itself, or elevation? Okay, so we know that r is defined as this, so let's copy this equation here. Radius as a function of plume location. Okay, we have found that as function of time, but we also want to find that as a function of location. So here we know that is r, and we also know the z value that is given there. So if we divide r by z, okay, where z we get from here, I can again simply copy this equation, right? So you see that it has common factors of f naught, t to the power half, etc. So that will very easily give us a simplified equation as r over z is equal to a over 3m. So that actually means that r simply increases with 3m z. So radius increases linearly with height. Okay, so this is the relation we have. Now we have to find the value of a and m, which are experimental constants. As you can see, for most of these equations we have f naught and we have parameters a and m. So a and m are experimental constant which we need to find out through experiment, and f naught is the given constant for a plume, so we don't have to worry about that. So to find the value of a and m, we will use this equation which we just derived, the radius equation, right? So radius here is a over 3m by z, and other equation that we are going to use is for z itself. So z is related to time as, let me copy this. All right, so you can see in these two equations now we have three things coming together. In first case we have radius as a function of z, and in second equation we have z as a function of time. So radius, height and time are related with each other using these three equations, right? So now in a lab experiment, if you perform such experiment and if you try to find the plume radius using lab setup or its elevation with time, we should be able to find the value of a and m. Okay, so in this case this second equation gives us, let's say, an equation of the form over t as 36 m square a cube 1 over 2 f naught 1 over 2, right? So if we just rearrange, this is what we get. Okay, so now going to this lab experiment which was performed by a scorer in 1997, right? These results are from, I think, scorer 1997, which we have also cited before. I'm just checking whether I'm writing the spelling correct. So there is no double R, it's just single R. Okay, so these results are from a scorer. And what you see here is, in the left hand image, this is the plume shape that was actually measured uh, using lab experiment. Okay, that is the plume shape, and this is the point of release. Okay, this, let's say that blue point, and Z is measured from here. Okay, and this part here is R. Okay, that is the radius of the plume, and you can see this here, this particular part is making an angle of theta, where theta is equal to 14 degree. Okay, that is found experimentally by measuring the shape or size of the plume with respect to the point of release. Okay, so if we use this, theta is 14 degree, that gives us 10 theta as 0.25. So basically R over Z is equal to 10 theta, that is 0.25. Okay, and from previous equation, this one we already have seen that R by Z is equal to A by 3m. So this means that A by 3m is equal to 0.25. Okay, this is one value we got using the shape of the plume or radius of the plume measured experimentally. Okay, now there is another data set we see here, where the values of Z square by t is plotted against square root of buoyancy. So here what you see in a square root is actually f naught. We are using the term f naught here, and these different individual data you see are for different experiment. So each experiment has different buoyancy value. Okay, and for each experiment, this Z value is measured against time and plotted here as Z square by time over square root of f naught. And you can see it very nicely follows a straight line, is a linear behavior, right? And if you try to find the slope of this straight line, that has a value of 5.8. Okay, this slope has a value of 5.8, and this is found purely experimentally by performing almost 15 to 20 experiment and plotting Z square by t versus square root of f naught. And what do we see here? The slope that we have found must be equal to 36 m square over a cube 1 by 2, where this is coming from here, right? This is the slope that we get there. So that is the same slope that we also get from this equation, from this plot. Okay, and this has a value of 5.8. Okay, so now we have got two equations. One is equation to the left, that is A by 3m, and one is equation to the right, and both of them have constants a and m involved, right? So now if we use these two equations, okay, A by 3m equal to 0.25 and 36 m square over a cube square root is 5.8. This gives us two different values or values of A as 2.54, and sorry, that is the value of m, and A as 1.9. Okay, so these values are found experimentally. Okay, and these, as we have seen here, this works for almost all plumes of different buoyancy flux, and that is why these values can be considered constant. And now you can use these values to define the plume radius, plume velocity, plume volume, reduced gravity, etc. Okay. All right, and finally, in the end, we can also try to see how the plume properties increases in time here. So let's say this is your time axis, and these are different axes like R, V, G prime, W bar, etc. And if you want to plot them, right? So radius, as we have seen, radius simply increases with z linearly. So sorry, not with z, we are trying to plot with time. So radius increases with square root of time, so it will look something like this. Okay, that is r as a function of square root of time, whereas volume, if you remember, it increases with t to the power 3 by 2, right? So that is how your volume will increase. And then we have g prime value, where g prime is decreasing with 3 by 2 times of time, and also we have the velocity that is decreasing with square root of time. So this is how your radius will decrease, and here we can also try to plot. Okay, this is how your g prime bar will decrease with t to the power 3 by 2. Okay, so this is how different values will increase or decrease from the z value or from the point of injection. So at t equal to 0, plume starts, and then slowly with increase in time, your volume increases, radius increases, and r value decreases, and your g prime value also decreases. So these are different patterns it will follow. Okay, so what we have seen in this particular case is the plumes generating because of a fixed buoyancy release, as we have seen in certain examples like in this volcanic plume. And now if you want to predict the behavior of this volcanic plume or other plumes with a fixed buoyancy release, you just need to know the initial buoyancy value, and that is this constant f naught. So if you know the f naught value here, if you are able to find f naught for the given buoyancy, you can predict all other parameters for that plume, like how quickly it will rise, what will be the rate of mixing, what will be the total volume of after a certain time, what will be its velocity, etc. Okay, so these are all the plume, and this plume what we have studied is in unstratified medium, where we are assuming that ambient density is constant, but then there are cases when ambient densities are also changing in case of stratified medium, but we will not study that part, and I leave that as a homework for you. You try to figure out what happens if the ambient density is stratified, and if you have to find the plume behavior in with fixed buoyancy release in stratified medium. Okay, so we'll stop the, so here we end the plume part, and next we will go to the gravity current, which is also a buoyancy driven flow, but it is of a little different kind. So here we conclude our lecture on plume, where we studied plume due to continuous injection, first in unstratified medium and then in stratified medium, and now we also studied plume due to fixed buoyancy release in unstratified medium. But then there is another case that is called plume with fixed buoyancy release in stratified medium, and that is something we are not doing, and it may be of your interest to work on it separately. Thank you.